Settle into the quiet space where long questions are allowed to linger. Let the present moment loosen its grip just slightly as attention drifts backward through layers of time measured not in years, but in memory. Tonight's inquiry is not urgent. It does not demand belief or disbelief. It only asks for patience and for a willingness to follow evidence where it leads, even if it leads somewhere unexpected. What follows is not a warning and not a revelation. It is an examination of a moment when the Earth itself changed direction, quickly, decisively, and left behind traces that still wait to be understood. After examining flood myths and ancient warnings, one question remains unavoidable. If a global reset truly occurred, where is the evidence? Not in stories alone, but in stone, in ice, in the physical record of the planet itself. Evidence that can be measured, dated, tested, and questioned. Evidence that exists whether or not anyone is looking for it. If this kind of investigation resonates with you, consider gently choosing to subscribe, not as a commitment, but as a quiet marker, a way of returning to these long questions whenever you feel drawn back to them, knowing the inquiry will continue patiently over time. Around 12,900 years ago, near the end of the last ice age, Earth entered a period scientists now call the Younger Dryas. By geological standards, it arrived almost without warning. Temperatures in the northern hemisphere dropped sharply, reversing a long trend of warming that had been steadily melting continental ice sheets. In places like Greenland, ice core records suggest this cooling occurred not over millennia, but within decades, and possibly within a single human lifetime. What makes the Younger Dryas remarkable is not simply that the climate cooled. Earth's climate has shifted many times before. What stands apart is the speed. Chemical signatures locked inside ancient ice show sudden changes in oxygen isotopes, markers that correspond to rapid drops in temperature. Dust concentrations increased. Snowfall patterns shifted. The atmosphere itself reorganized in a way that defies the slow, gradual rhythms often associated with natural climate cycles. Sea levels responded as well. Vast quantities of meltwater, released from retreating ice sheets, appear to have flooded into the North Atlantic. This influx of freshwater may have disrupted ocean circulation systems that distribute heat around the planet. The result was a cascade effect. Cooler oceans, altered winds, expanding ice, and collapsing ecosystems followed in sequence, each reinforcing the next. Across continents, environments changed faster than many species could adapt. Large mammals that had survived previous climatic swings began to vanish from the fossil record. In some regions, archaeological evidence suggests that early human cultures were forced to abandon established patterns of movement and survival, adjusting to landscapes that no longer behaved as expected. The Younger Dryas is not controversial because it happened. The evidence for its occurrence is firmly established. It is controversial because of how fast it happened. Such rapid change challenges traditional models that rely on slow, incremental forces. It raises a quieter, more difficult question. What kind of trigger is capable of pushing a planetary system past a threshold so suddenly, leaving behind a clear line in time where conditions before and after no longer resemble each other? That question does not lead immediately to answers, but it does mark a boundary. On one side lies a world steadily emerging from ice. On the other, a sudden return to cold, instability, and uncertainty. And it is along that boundary that the investigation must continue, following the evidence layer by layer, deeper into the moment when Earth abruptly changed course. That boundary, once crossed, does not announce itself with spectacle. It reveals itself quietly in measurements taken decades apart, in thin layers of ice and sediment that record change without interpretation. To understand the Younger Dryas, researchers first had to recognize that these layers were not anomalies, but signals. Signals that something in Earth's climate system had shifted rapidly and then remained locked in that altered state, for more than 1,000 years. The Younger Dryas marks a return to near-glacial conditions at a time when the planet should have continued warming. Prior to its onset, temperatures were rising, ice sheets were retreating, and ecosystems were expanding northward. The trajectory appeared consistent with previous deglaciation phases observed in Earth's long climate history. Then, abruptly, that trajectory reversed. Ice core data provides the clearest window into this reversal. Cylinders drilled from the Greenland ice sheet preserve annual snowfall like pages in a book. Within these layers, scientists measure isotopes of oxygen and hydrogen, microscopic traces that reflect the temperature of the atmosphere at the time the snow fell. At the boundary marking the start of the Younger Dryas, those isotope ratios shift sharply. The change is not gradual. It is immediate enough to be resolved year by year. This same pattern appears across multiple ice cores, collected from different locations and analyzed independently. The consistency of the signal strengthens its credibility. It suggests that the cooling was not regional noise, but part of a broader hemispheric and possibly global event. Dust concentrations increase in these layers as well, indicating stronger winds and drier conditions, further evidence of a reorganized climate system. Beyond the ice, the signal continues. Lake sediments across Europe and North America show sudden changes in pollen composition. Forest species retreat, cold-tolerant plants expand. These transitions occur too quickly to reflect slow ecological succession. They indicate environments responding under pressure, adjusting to conditions that changed faster than long-term adaptation normally allows. Ocean records tell a similar story. Marine sediments reveal shifts in plankton species that correspond to colder surface waters. Chemical tracers point to disruptions in thermohaline circulation, the global conveyor belt of ocean currents that moves heat from the equator toward the poles. When this circulation weakens or stalls, regional climates can shift rapidly, even if the overall energy balance of the planet changes only slightly. What emerges from these independent lines of evidence is not a single dramatic event, but a convergence. Ice, ocean, land, and atmosphere all register change within the same narrow window of time. The Younger Dryas was not a slow descent into cold. It was a step change, a rapid reconfiguration of systems that are usually stable precisely because they change so slowly. This realization reframes the central problem. The question is no longer whether the Younger Dryas occurred or whether its effects were significant. The question becomes one of causation. What mechanism or combination of mechanisms could override the inertia of Earth's climate system so quickly, forcing it into a colder state against the prevailing trend? And once that question is asked, the investigation naturally turns from description to explanation, from what happened to how it could have happened at all. How it could have happened is where restraint becomes essential. The Younger Dryas does not point to a single obvious cause, but to a set of constraints imposed by the evidence itself. Any proposed explanation must account for speed, scale, and synchronization. It must explain how cooling began almost simultaneously across vast regions, why it persisted for more than a millennium, and how it eventually ended just as abruptly as it began. The most widely discussed explanation begins with water. As the great ice sheets of North America retreated, enormous volumes of meltwater accumulated along their margins. One such body, often referred to as a proglacial lake, held back by ice rather than land, contained more fresh water than all modern lakes combined. If released suddenly, this water would have flowed into the North Atlantic, diluting seawater and reducing its density. Ocean circulation depends on density differences. In the North Atlantic, cold, salty water normally sinks, driving a global system of currents that redistribute heat. A sudden influx of fresh water could disrupt this process, weakening or halting the circulation. Climate models show that such a disruption can produce rapid cooling across the North Atlantic region, with secondary effects extending much farther. There is physical evidence supporting this scenario. Geological features indicate large-scale meltwater water routing events, where water abruptly changed course as ice dams failed or retreated. Sediment deposits along ancient drainage paths suggest rapid flow rather than gradual release. Marine records show changes consistent with reduced deep water formation during the Younger Dryas interval, yet this explanation, while compelling, is incomplete. It explains regional cooling well, but struggles to account for the global coherence of the signal. Similar timing appears in records from regions far removed from the North Atlantic, including parts of the Southern Hemisphere. This raises the possibility that ocean circulation disruption may have been a major factor, but not the only one. Volcanism has also been considered. Large eruptions can inject aerosols into the atmosphere, reflecting sunlight and cooling the surface. However, volcanic cooling is typically short-lived, measured in years rather than centuries. While eruptions may have contributed to short-term variability, they do not easily explain a sustained 1,000-year return to near-glacial conditions. This leaves researchers with a narrowing field of possibilities. The Younger Dryas appears to require a trigger capable of initiating rapid change, combined with feedback strong enough to maintain it. Once cooling began, expanding ice and snow would have reflected more sunlight, reinforcing the cold. Changes in vegetation would have altered carbon storage and atmospheric composition. Each response amplified the initial disturbance. What remains uncertain is the origin of that disturbance. Whether it was initiated internally, through Earth's own climate dynamics, or externally, through an event imposed from outside the system, is still debated. The evidence does not yet force a single conclusion. Instead, it defines a boundary of plausibility within which explanations must operate. And it is at this boundary that the investigation becomes more delicate, because to explore certain possibilities requires confronting ideas that sit at the edge of conventional frameworks, ideas that are neither dismissed by evidence nor fully supported by it. The next step, then, is not to assert a cause, but to examine one of the most debated possibilities with the same discipline applied to all the others. Among those debated possibilities, one stands apart not because it is dramatic, but because it is difficult to test. The idea that an external cosmic event may have played a role in triggering the Younger Dryas has remained controversial precisely because it demands an unusually high standard of evidence. Extraordinary claims are not evaluated by how striking they sound, but by whether physical traces remain where such an event would be expected to leave them. The so-called cosmic impact hypothesis proposes that Earth encountered debris from space around the onset of the Younger Dryas. Not necessarily a single large asteroid, but possibly fragments from a disintegrating body or material associated with a dense stream of cosmic debris. If such material entered the atmosphere or struck ice sheets, it could have released enormous energy in a very short time, initiating widespread environmental disruption. Supporters of this hypothesis point to specific markers found at the Younger Dryas boundary. In sediment layers across multiple continents, researchers have reported elevated concentrations of microscopic spherules, materials formed under extreme heat. Some samples also show anomalies in elements that are rare at Earth's surface, but more common in extraterrestrial material. These findings are clustered within a narrow time interval, suggesting a sudden deposition rather than a slow accumulation. Additional attention has focused on nanodiamonds, tiny crystalline structures that can form under intense pressure and temperature. In some studies, these particles appear in higher concentrations at the same boundary layer associated with the onset of cooling. Their presence has been interpreted as consistent with high-energy events, though their exact formation pathways remain debated. Critically, none of these markers alone constitute definitive proof of an impact. Each has alternative explanations rooted in terrestrial processes. Wildfires, volcanism, and normal geochemical variation can produce similar signatures under certain conditions. This ambiguity is why the hypothesis remains unresolved. The evidence suggests something unusual occurred, but not yet something unambiguous. What makes the discussion scientifically meaningful is not the certainty of the claim, but the rigor of the debate. Independent teams have attempted to replicate these findings, sometimes confirming them, sometimes failing to do so. Discrepancies in sampling methods, dating precision, and regional geology complicate direct comparisons. As a result, the hypothesis exists in a state of tension, neither accepted nor discarded. This tension mirrors the broader challenge of understanding abrupt climate events. The Earth system is capable of non-linear behavior, where small disturbances can trigger disproportionate responses if critical thresholds are crossed. A cosmic trigger, if it occurred, may not have been the sole cause, but a catalyst that pushed an already sensitive system into a new state. At this point in the investigation, certainty remains out of reach. What can be said with confidence is narrower but still significant. Around 12,900 years ago, multiple systems recorded a sudden disruption. The speed of that disruption is the central fact that any explanation must address. Whether the trigger came from melting ice, shifting currents, or the wider cosmic environment, the Younger Dryas stands as a reminder that stability in complex systems is often conditional, and it is from this recognition that the inquiry naturally extends forward. Because if rapid change was possible once, under conditions not entirely understood, then the deeper question is not only what happened then, but how often such thresholds may have been crossed throughout Earth's longer history. That deeper question moves the focus away from singular causes and toward patterns. The Younger Dryas is not examined in isolation, but as part of a class of events known as abrupt climate shifts. These are intervals where Earth systems reorganize far faster than the slow forces that usually govern them. When viewed this way, the Younger Dryas becomes a case study in sensitivity, revealing how close to instability the planet may have been at the end of the last ice age. One of the most striking features of the Younger Dryas is how sharply it ends. After more than 1,000 years of cold conditions, temperatures rise again with remarkable speed. Ice core records show a rapid return to warmer conditions, in some regions within a few decades. This symmetry, a sudden descent followed by a sudden recovery, suggests that whatever mechanisms drove the cooling were capable of switching states rather than drifting gradually. Such behavior is consistent with threshold-driven systems. In climate science, thresholds represent points beyond which feedbacks dominate. Once crossed, the system reorganizes itself into a new equilibrium. In the case of the Younger Dryas, ocean circulation is often proposed as one such threshold system. A disruption may have pushed it into a weakened mode, while a later change restored it just as quickly. Evidence from ocean sediments indicates that deep water formation in the North Atlantic resumed near the end of the Younger Dryas. Salinity levels increased, currents strengthened, and heat transport recovered. This would have initiated rapid warming, melting ice, and reversing many of the ecological changes that had taken place during the cold interval. The speed of recovery reinforces the idea that the system had not been slowly rebuilding, but was instead waiting for conditions to cross a critical line. Human populations living through this transition would have experienced dramatic environmental shifts within a few generations. Archaeological records suggest changes in settlement patterns, tool technologies, and subsistence strategies that align with these climatic oscillations. While the data does not imply global societal collapse, it does indicate periods of stress, adaptation, and reorganization closely tied to environmental instability. Importantly, the Younger Dryas does not require a catastrophic narrative to remain significant. Its importance lies in what it demonstrates about Earth's capacity for rapid change. The event shows that under certain boundary conditions, climate systems can respond quickly, decisively, and in ways that challenge assumptions of gradualism. This realization reframes the relationship between ancient narratives and physical evidence. Rather than asking whether myths describe a specific event, the more productive question becomes whether human memory could preserve impressions of sudden environmental disruption. Not precise mechanisms or dates, but experiences of instability, loss, and abrupt change pass down in symbolic form. The Younger Dryas does not confirm ancient reset stories, nor does it dismiss them. It occupies a middle ground, where physical evidence establishes that rapid, large-scale change did occur, while interpretation remains open. And it is within that space, between certainty and speculation, that the series continues, because the question ahead is not only whether the past holds examples of sudden resets, but whether such dynamics are inherent features of the Earth system itself, repeating whenever thresholds are approached once again. Those inherent features bring the investigation back to the present, not as a warning, but as a context. The Younger Dryas reminds researchers that Earth's climate does not always respond in smooth curves. It can pause, reverse, and accelerate when conditions align. This understanding has reshaped how scientists interpret both ancient data and modern observations, encouraging closer attention to signs of instability rather than averages alone. One of the lasting impacts of Younger Dryas research is methodological. It forced climate science to improve its resolution. Events unfolding over decades cannot be understood with tools designed to measure changes over millennia. Ice cores, sediment layers, and high-precision dating techniques have since revealed other abrupt events scattered throughout Earth's past, smaller in scale but similar in character. These discoveries suggest that the Younger Dryas was not unique, but unusually well-preserved and well-timed within human history. Its proximity to the emergence of agriculture and more complex human societies gives it particular significance. It occurred at a moment when human populations were becoming more regionally established, more dependent on predictable environments. Sudden instability at such a moment would have left a strong imprint on behavior and memory. Yet the evidence still resists simple conclusions. The Younger Dryas does not point cleanly to a single cause, nor to a single outcome. It represents convergence, multiple stressors acting together, feedbacks reinforcing each other, and a system already near a tipping point. Whether meltwater, atmospheric shifts, or external inputs played the initiating role may ultimately matter less than the recognition that the system was vulnerable. This perspective tempers speculation without dismissing it. It allows room for unresolved questions while grounding them in physical constraints. The cosmic impact hypothesis, for example, remains under investigation not because it explains everything, but because it addresses the problem of speed. At the same time, internal mechanisms address persistence. Together, they illustrate how complex events may arise from layered causes rather than singular triggers. As the record improves, so does the ability to test these ideas. New drilling projects, refined dating techniques, and broader geographic sampling continue to narrow uncertainties. Each refinement reduces the space available for unfounded claims while sharpening the remaining questions. The process is slow, deliberate, and cumulative, mirroring the patience required to interpret events that unfolded so quickly. In this way, the Younger Dryas becomes less about answers and more about framework. It establishes that rapid planetary change is not hypothetical. It has occurred, it is documented, and it is measurable. What remains is to understand the conditions under which such change becomes possible. And it is precisely this unresolved boundary between stability and sudden transition that sets the stage for the next chapter. Because to explore that boundary fully, the investigation must look beyond Earth alone, toward the wider environment through which the planet moves, and consider whether forces beyond the atmosphere and oceans may periodically intersect with Earth's internal rhythms. Looking outward does not mean abandoning rigor. It means expanding context. Earth does not exist in isolation, and its history is shaped not only by internal processes, but by its position within a dynamic solar system. Orbital variations, solar output, and the flux of material moving through near-Earth space are all measurable influences, even if their effects are unevenly distributed through time. The idea that external factors could intersect with internal vulnerabilities is not new. Milankovitch cycles, for example, describe how slow changes in Earth's orbit influence long-term climate patterns. These cycles operate predictably over tens of thousands of years and help explain the pacing of ice ages. What they do not explain well are sudden reversals like the Younger Dryas, events that occur far more quickly than orbital forcing alone would suggest. This discrepancy has led researchers to consider whether short-duration external disturbances could act as triggers when internal systems are already near critical thresholds. In this framework, an external input does not need to be catastrophic to be consequential. It only needs to arrive at the right moment, when feedbacks are primed to amplify even modest changes. Astronomical records indicate that Earth periodically encounters regions of increased debris density as it moves through the galaxy. Most of this material is harmless, burning up in the atmosphere as meteors. Occasionally, larger fragments reach the surface. While impacts of civilization-ending scale are rare, smaller events are far more frequent and can still inject energy, dust, and aerosols into the atmosphere. If such an encounter coincided with a climate system already destabilized by melting ice and disrupted circulation, the combined effect could exceed the sum of its parts. This is not an assertion, but a conditional possibility grounded in systems behavior. Complex systems do not require overwhelming force to change state, only the right perturbation at the right time. The Younger Dryas continues to be studied within this broader systems framework. Rather than asking whether one cause can explain everything, researchers increasingly ask how multiple influences might align. Internal feedbacks, external inputs, and chance timing all become variables in a probabilistic understanding of the past. This approach also reframes uncertainty. Lack of definitive proof for a single trigger does not imply lack of explanation. It reflects the limits of preservation and resolution when studying events that occurred nearly 13,000 years ago. Not all signals survive. Not all traces are evenly distributed. Absence of evidence in one region does not invalidate presence in another. What remains consistent is the pattern. A rapid shift occurred. Multiple systems recorded it. Recovery was equally abrupt. These features define the event more strongly than any individual hypothesis. They form the core against which all explanations are measured. As the investigation continues, attention turns toward how such patterns may repeat, not identically, but in form. The Younger Dryas becomes a reference point, a benchmark for understanding how quickly Earth can change when thresholds are crossed. And it is from this reference point that broader questions emerge. Questions not only about the past, but about the underlying architecture of change itself. That underlying architecture is what ultimately gives the Younger Dryas its lasting significance. Beyond dates and mechanisms, it reveals something fundamental about how Earth behaves under stress. Stability, it suggests, is not a permanent condition, but a temporary balance maintained until enough pressures align to disrupt it. When that balance fails, change can unfold far faster than intuition expects. This insight has reshaped how scientists interpret the end of the last ice age. Rather than a smooth transition from cold to warm, the period now appears punctuated by pauses, reversals, and accelerations. The Younger Dryas stands out because it is the clearest and most abrupt of these interruptions, but it is embedded within a broader pattern of climatic variability that challenges linear narratives. From this perspective, the event is less an anomaly and more a demonstration. It shows that Earth's climate system contains internal switches, states that can flip when conditions cross certain thresholds. These switches are governed by feedbacks involving ice cover, ocean circulation, atmospheric composition, and energy balance. Once engaged, they can hold the system in a new configuration until counteracting forces become strong enough to reverse them. The archaeological record, when viewed alongside this framework, takes on added depth. Human groups living at the edge of glacial retreat were not passive observers of a stable world. They occupied landscapes in flux where resources shifted, coastlines moved, and ecosystems reorganized within spans short enough to be experienced directly. Cultural flexibility, mobility, and innovation during this period may reflect adaptation to precisely this kind of instability. This does not require invoking collapse or global catastrophe. It requires acknowledging variability. A world capable of sudden cooling is a world in which planning, memory, and tradition must remain adaptable. Over generations, such experiences could be encoded not as technical explanations, but as narratives emphasizing disruption, loss, and renewal. The Younger Dryas therefore occupies a unique position between geology and memory. It is firmly anchored in physical evidence, yet close enough to the rise of complex human societies to invite reflection on how environmental change is perceived and remembered. It does not validate specific ancient stories, but it demonstrates that the conditions for sudden, widespread disruption did exist. As this chapter of the 3i Atlas series draws toward its close, the central conclusion remains measured. The Younger Dryas is not controversial because it happened. It is controversial because of how quickly it unfolded, and because that speed forces a reconsideration of what Earth is capable of when pushed beyond equilibrium. In the next chapter, the focus will narrow rather than expand. The investigation will turn directly to the most debated possibility raised here, examining whether evidence for cosmic involvement can withstand the same disciplined scrutiny applied to all other explanations, and what that debate reveals about the limits of certainty when studying sudden resets in deep time. That scrutiny begins by narrowing definitions. When researchers discuss cosmic involvement, they are not invoking distant stars or abstract forces, but specific, testable interactions between Earth and its immediate space environment. The question is not whether space influences Earth, that much is already established, but whether such influences can intersect with climate systems in ways that leave lasting, measurable effects. To evaluate this, scientists return again to timing. The onset of the Younger Dryas is dated with increasing precision, converging around a narrow window roughly 12,900 years ago. Any proposed external trigger must align closely with this boundary. It must also produce effects consistent with what is observed in the geological and biological record without exceeding it. One of the challenges lies in scale. Large impacts leave unmistakable signatures, craters, global ejecta layers, and mass extinctions. None of these appear at the Younger Dryas boundary in a form that would suggest a single, massive collision. This absence immediately constrains what kinds of cosmic events remain plausible. Attention therefore shifts to smaller-scale phenomena. Airbursts, fragmenting objects, or encounters with dense debris streams could deliver energy and material without producing a single dominant crater. Such events are known to occur. Modern examples, though limited in scale, demonstrate that significant energy can be released in the atmosphere without direct surface impact. If such an event occurred over ice sheets or oceans, physical traces could be subtle and unevenly preserved. Ice would melt and refreeze. Water would absorb and redistribute energy. Atmospheric effects could propagate widely, even if the initiating interaction was localized. This uneven preservation is one reason the evidence remains fragmentary and contested. The scientific response to this uncertainty has been methodological rather than rhetorical. Claims are tested against independent data sets. Chemical markers are cross-checked. Stratigraphic layers are re-examined. Chronologies are refined. Each iteration either narrows or widens the range of plausible explanations. What emerges is not consensus, but constraint. The Younger Dryas appears increasingly bounded by what could and could not have happened. Extreme scenarios fall away under scrutiny. Modest but well-timed disturbances remain under consideration. The debate persists not because evidence is ignored, but because it resists simple resolution. In this sense, the Younger Dryas functions as a case study in scientific restraint. It demonstrates how complex events are approached when data is incomplete, but consequences are significant. Rather than forcing closure, the investigation remains open, guided by evidence, limited by uncertainty, and shaped by the recognition that Earth's history does not always provide clean answers. And it is within that disciplined uncertainty that the broader implications begin to surface. Because if abrupt change can occur without singular, overwhelming causes, then sensitivity itself becomes the key variable. Understanding when and why systems become sensitive may ultimately matter more than identifying every trigger that has ever crossed their path. Sensitivity, in this context, refers to how close a system is to a threshold beyond which small influences can produce large responses. The end of the last ice age was a period marked by precisely this condition. Vast ice sheets were retreating, sea levels were rising, and ocean circulation patterns were adjusting to a rapidly changing distribution of freshwater. The system was dynamic, not settled, and therefore more responsive to disturbance. This framing helps reconcile why the Younger Dryas could occur without a single dominant cause. Instead of searching for an overwhelming force, researchers consider whether multiple moderate influences converged at a moment of instability. Meltwater pulses, atmospheric changes, and possible external inputs may have overlapped in time, each insufficient alone, but together capable of shifting the system into a colder state. Climate models increasingly support this interpretation. Simulations show that when ocean circulation is weakened by freshwater input, even small additional perturbations can prolong or intensify cooling. Feedbacks involving sea ice expansion and increased reflectivity amplify the initial change, allowing it to persist far longer than the original disturbance. The end of the Younger Dryas reinforces this view. As conditions gradually shifted, salinity levels recovered, circulation strengthened, and the system crossed back over its threshold. Warming resumed quickly, not because forces slowly accumulated, but because the balance tipped once again. The speed of both onset and recovery reflects the same underlying sensitivity. This perspective also clarifies why abrupt events are unevenly distributed through Earth's history. Not every period is equally vulnerable. Long stretches of relative stability can absorb disturbances with little effect. Other intervals, particularly those marked by transition, are far more responsive. The Younger Dryas occurred during such a transition, when the climate system was already reorganizing on multiple fronts. Understanding this distinction is crucial. It shifts emphasis from rare external catastrophes to more common states of internal vulnerability. While external factors may still matter, their influence depends heavily on the condition of the system they encounter. Timing becomes as important as magnitude. This insight does not diminish the significance of the Younger Dryas. It deepens it. The event becomes evidence that Earth's climate contains built-in tipping behavior, capable of rapid shifts when conditions align. Such behavior is not an exception to the rules of the system, but part of how the system operates. As the investigation continues, attention moves toward identifying these vulnerable intervals elsewhere in the record. By doing so, researchers hope to better understand not only what happened 12,900 years ago, but how often similar sensitivities may have shaped Earth's past, quietly and decisively, long before they were ever measured. Those vulnerable intervals are often difficult to recognize in advance, even with detailed data. They do not announce themselves through a single variable, but through convergence. Gradual warming, shifting precipitation, melting ice, and changing circulation patterns each represent manageable adjustments on their own. It is only when they overlap that the system's resilience begins to thin. The Younger Dryas illustrates this convergence clearly. The planet was emerging from a glacial maximum, a process that inherently destabilizes climate equilibria. Ice sheets that had persisted for tens of thousands of years were retreating unevenly. Freshwater inputs were episodic rather than constant. Atmospheric greenhouse gas concentrations were rising, but not uniformly across hemispheres. These uneven changes created regional imbalances that the global system had to absorb. In such conditions, feedbacks matter more than forcings. Ice cover reflects sunlight, reinforcing cooling. Vegetation changes alter surface reflectivity and carbon storage. Ocean circulation redistributes heat unevenly. Each feedback can either dampen or amplify change depending on context. During the Younger Dryas, amplification appears to have dominated. One of the most revealing aspects of the event is how clearly it is recorded across independent archives. Ice cores, lake sediments, marine records, and biological proxies all point to disruption within the same narrow time frame. This coherence strengthens the case that the Younger Dryas was not an artifact of measurement or regional anomaly, but a real system-wide transition. At the same time, differences between regions remind researchers that abrupt change is rarely uniform. Some areas cooled dramatically, others less so. Some ecosystems collapsed, others adapted. This variability underscores the importance of local conditions even during global-scale shifts. It also complicates interpretation, as no single record captures the full picture. As evidence accumulates, the Younger Dryas increasingly serves as a reference event. It provides a concrete example against which other abrupt changes are compared. When similar patterns appear elsewhere in the record, sudden isotope shifts, rapid ecological turnover, synchronized transitions, they are evaluated through the lens established by this well-studied interval. What emerges from this comparative approach is a more nuanced understanding of change. Abrupt events are not anomalies imposed from outside a stable system. They are expressions of internal dynamics under stress. External influences may still act as triggers, but they do so by interacting with vulnerabilities that already exist. This understanding sets a boundary on speculation while preserving open inquiry. It allows discussion of debated hypotheses without elevating them beyond what evidence supports. It also emphasizes process over narrative, focusing attention on how systems behave rather than on dramatic singular causes. And in doing so, it prepares the ground for the final question of this chapter. Not whether the Younger Dryas was a reset, but whether it reveals a broader principle. That rapid, large-scale change may be an inherent feature of Earth's history, emerging whenever balance gives way to sensitivity, and thresholds quietly give way beneath the surface. That broader principle reframes how the term reset is understood. In scientific terms, the Younger Dryas does not represent a complete restart of Earth's systems, but a reorganization. Energy flows continued. Life persisted. Yet the rules governing climate behavior shifted abruptly, forcing ecosystems and human populations to respond to a new configuration with little warning. This distinction is important because it separates evidence from interpretation. A reset, in this context, is not destruction followed by rebirth, but a sudden change in boundary conditions. Temperature gradients, precipitation patterns, and seasonal reliability all altered within a narrow window. For societies dependent on predictable cycles, such changes would have been experienced as profound disruption, even without total collapse. The archaeological record supports this interpretation cautiously. In several regions, material cultures show signs of discontinuity around the Younger Dryas onset. Settlement patterns shift, tool assemblages change, resource use adapts. These signals do not point to global abandonment, but they do suggest stress and rapid adjustment in response to environmental change. Crucially, these cultural transitions are asynchronous. They do not occur everywhere at once, nor do they take the same form. This mirrors the climatic record, where the Younger Dryas expresses itself differently depending on geography. Such variability reinforces the idea that large-scale change does not erase local agency. Instead, it reshapes the constraints within which adaptation occurs. From a systems perspective, this is what makes the Younger Dryas so instructive. It demonstrates that abrupt change does not require uniform impact to be transformative. Shifts in averages, even if unevenly distributed, can alter the viability of existing strategies and force innovation or migration. This insight also tempers how ancient narratives are approached. Rather than treating them as literal records of singular events, they can be understood as cultural responses to instability. Memory does not preserve isotopic ratios or ocean circulation patterns. It preserves experiences: cold where warmth was expected, scarcity where abundance had been known, uncertainty replacing rhythm. Seen this way, the Younger Dryas does not validate myth, nor does it dismiss it. It provides a physical context in which such memories could form and persist. It anchors speculation to evidence without demanding equivalence between story and data. As this chapter continues, the focus tightens once more. Having established that rapid, large-scale reorganization did occur, the remaining task is to clarify what this implies for understanding Earth's past. Not as a sequence of smooth transitions, but as a landscape shaped by thresholds, where long periods of relative stability are occasionally interrupted by swift, decisive change. Those swift interruptions complicate how history is usually visualized. Timelines often imply continuity, a gradual unfolding where cause and effect move predictably forward. The Younger Dryas disrupts that expectation. It inserts a sharp inflection point into what would otherwise appear as a smooth climatic curve, reminding researchers that time does not always behave evenly in natural systems. From a geological perspective, such inflection points are rare but consequential. They compress change into intervals so brief that they stand out even against the vastness of deep time. This compression is why the Younger Dryas attracts continued attention. It is not merely another cold phase, but a moment when the pace of change itself accelerated beyond the norm. This acceleration forces a reassessment of causality. When change is slow, tracing causes is relatively straightforward. When change is fast, overlapping signals blur lines of origin. Meltwater pulses coincide with atmospheric shifts. Ecological responses lag behind physical forcing. Human adaptation unfolds on yet another timescale. Untangling these threads requires careful separation of sequence from consequence. One way researchers approach this challenge is by focusing on order rather than explanation. What changed first? What followed? What responded? Ice cores suggest cooling preceded many ecological shifts. Ocean circulation indicators change alongside temperature. Biological responses trail physical ones. This ordering helps constrain models even when mechanisms remain debated. Within this framework, the Younger Dryas begins to look less like an anomaly and more like a stress test. It reveals how the climate system behaves when pushed away from equilibrium. It shows which components respond quickly and which resist change. It highlights feedbacks that amplify disturbance and those that eventually restore balance. Importantly, it also reveals limits. The cooling did not continue indefinitely. The system did not spiral into a permanent glacial state. After roughly 12 centuries, conditions reversed. This tells researchers that stabilizing forces remained active, even if temporarily overridden. The climate system bent sharply, but it did not break. This balance between disruption and recovery is central to why the Younger Dryas remains relevant. It demonstrates that resilience and vulnerability coexist. The same system capable of rapid reorganization is also capable of rapid stabilization once conditions allow. As the evidence continues to accumulate, the Younger Dryas stands not as a mystery demanding a single answer, but as a reference point for understanding how Earth transitions between states. It invites a quieter conclusion, that the planet's history is written not only in long trends, but in brief moments when balance shifts. Memory is formed, and the future quietly takes a different path. That different path becomes clearer when the Younger Dryas is placed alongside other abrupt events identified in the climate record. While few match its scale or clarity, several share its defining characteristic: speed. Rapid temperature shifts, sudden changes in precipitation, and swift ecological responses appear intermittently throughout Earth's history, often clustered around periods of broader transition. These events suggest that abrupt change is not random. It tends to occur when systems are already in motion, when long-term forces have reduced stability and narrowed the margin for disturbance. In this sense, the Younger Dryas can be seen as part of a recurring pattern rather than an isolated interruption. Each occurrence differs in detail, but the underlying behavior remains recognizable. This recognition has important implications for how evidence is interpreted. Rather than searching for a unique trigger that explains everything, researchers increasingly focus on identifying conditions that make rapid change possible. Ice volume, ocean stratification, atmospheric composition, and solar input all become variables in a larger equation of sensitivity. The Younger Dryas provides unusually strong constraints on this equation because of its precise timing and global footprint. Its onset, duration, and termination are all sharply defined relative to most events in the deep past. This precision allows hypotheses to be tested against a clear benchmark. Explanations that cannot reproduce its speed or persistence are gradually set aside. Over time, this process has refined understanding rather than narrowed it. The event is no longer viewed as a puzzle awaiting a single missing piece, but as a complex interaction whose components are increasingly well described. What remains uncertain is not whether the change occurred, but how the balance between internal dynamics and external influence should be weighted. This uncertainty is not a weakness of the evidence. It is a reflection of the limits imposed by time and preservation. Not all signals survive, not all processes leave unambiguous traces. Yet enough remains to establish a clear conclusion. Earth is capable of reorganizing itself rapidly when conditions align. As this chapter approaches its closing perspective, the Younger Dryas stands as both evidence and caution. Evidence that sudden, large-scale change has occurred without warning in the past. Caution against assuming that stability is the default state rather than a temporary outcome of balance. In the end, the Younger Dryas does not demand belief in any single narrative. It demands attention. Attention to speed, attention to thresholds, and attention to the quiet fact that beneath long periods of calm, the potential for rapid transformation has always been present, waiting for the moment when balance gives way. That potential for rapid transformation reframes how the end of the last ice age is understood. Instead of a simple conclusion to a cold epoch, it appears as a period of negotiation between opposing forces. Warming trends pressed forward, cooling mechanisms resisted. The Younger Dryas represents a moment when resistance briefly prevailed, reshaping conditions across much of the planet. From this perspective, the event underscores the importance of feedback dominance. Climate does not change because a single factor acts alone, but because feedbacks either reinforce or counteract initial influences. During the Younger Dryas, reinforcing feedbacks appear to have aligned in favor of cooling. Ice expansion increased reflectivity. Ocean circulation weakened. Atmospheric circulation adjusted accordingly. Each response supported the next. The eventual termination of the Younger Dryas signals a reversal of that alignment. Feedbacks that had sustained cold conditions weakened, while stabilizing forces regained influence. This shift did not require a dramatic external event. It required conditions to move just far enough for the balance to tip back. Such behavior highlights a central lesson. The magnitude of change does not always correspond to the magnitude of the trigger. Small shifts, when timed precisely, can cascade through interconnected systems. This principle applies across scales, from climate to ecosystems to human societies. The Younger Dryas therefore serves as a reminder of proportionality. It cautions against assuming that dramatic outcomes require dramatic causes. At the same time, it cautions against dismissing subtle influences simply because they are difficult to detect. This balanced view is what gives the event its enduring scientific value. It anchors speculation to evidence while leaving space for unresolved questions. It acknowledges complexity without resorting to oversimplification. In doing so, it preserves the Younger Dryas as a reference point rather than a conclusion. As the chapter concludes, the focus shifts from explanation to implication. The Younger Dryas demonstrates that Earth's climate has thresholds, and that crossing them can produce rapid, widespread effects. This is not an abstract insight. It is a documented feature of the planet's history. With that understanding in place, the series moves forward. The next chapter will examine the most debated hypothesis raised by this event in greater detail, not to confirm it, but to test its limits. By doing so, it continues the broader inquiry into how sudden resets, whether internal or external in origin, fit within the long and intricate history of Earth's changing state. Testing those limits requires returning to first principles. In science, a hypothesis gains strength not by how well it fits a story, but by how well it survives constraint. The Younger Dryas has imposed unusually strict constraints because its timing, duration, and effects are now defined with considerable precision. Any explanation that remains viable must operate within those boundaries. One of the most important constraints is energy balance. The cooling observed during the Younger Dryas was substantial, but not absolute. Ice sheets advanced, but did not return to full glacial extent. Ecosystems reorganized, but life persisted across latitudes. This indicates a shift in distribution rather than a collapse of planetary energy input. Whatever initiated the event altered how energy was moved and stored, not how much ultimately reached the Earth. This distinction narrows the field considerably. It favors mechanisms that redistribute heat, such as ocean and atmospheric circulation, over those that dramatically reduce incoming solar radiation for extended periods. It also suggests that feedbacks, once engaged, did much of the work in sustaining the cold interval. Another constraint lies in duration. The Younger Dryas lasted roughly 1,200 years, far longer than the immediate effects of most short-lived disturbances. This persistence implies that once the system entered its altered state, internal processes maintained it. A trigger, if present, needed only to initiate the transition, not to sustain it. These constraints do not eliminate debated hypotheses, but they contextualize them. External events, if involved, must be consistent with subtle initiation rather than prolonged forcing. Internal dynamics must explain both the maintenance of cold conditions and the abrupt recovery that followed. The strength of the Younger Dryas record is that it allows such distinctions to be drawn. Few events in deep time offer this level of clarity. As a result, the discussion surrounding it has matured. Early debates focused on whether certain ideas were plausible at all. More recent work asks how much each mechanism could realistically contribute. This shift marks progress. It reflects a movement away from binary explanations toward layered ones. The Younger Dryas is increasingly understood as the product of interaction rather than dominance, of convergence rather than singular cause. As this perspective settles, the event's role within the series becomes clearer. It is not presented as proof of a universal pattern, but as evidence that sudden reorganization is possible under specific conditions. The question ahead is how often those conditions have arisen, and whether they have left comparable signatures elsewhere in Earth's history, waiting to be recognized. Recognizing comparable signatures elsewhere requires careful comparison rather than assumption. The Younger Dryas provides a template, not a blueprint. Its defining traits, rapid onset, system-wide impact, and abrupt termination, become criteria against which other events are evaluated. When similar patterns appear, they invite attention, but not automatic equivalence. Researchers have identified several abrupt climate shifts in the geological record that share aspects of this template. Some occur during earlier glacial cycles, others during transitions between stable states. Many are shorter-lived or less intense, but their existence reinforces a central point. Earth's climate does not change exclusively through slow accumulation. It also changes through punctuated adjustments. These punctuations tend to cluster around moments of imbalance, periods when ice volume, greenhouse gas concentrations, or ocean circulation are already shifting, appear more susceptible to rapid reorganization. This pattern echoes what is observed during the Younger Dryas, strengthening the interpretation that vulnerability, rather than anomaly, is the key factor. Importantly, not all abrupt events leave equal traces. Preservation depends on location, sedimentation rates, and subsequent disturbance. Some events may be clearly visible in ice cores but muted in ocean sediments. Others may be evident in biological records, but less so in geochemical proxies. This uneven visibility complicates efforts to construct a complete catalog of sudden change. Despite these limitations, the cumulative evidence points toward a climate system capable of multiple modes. It can remain stable for long intervals, absorbing disturbance, and then shift rapidly when thresholds are crossed. The Younger Dryas is one of the clearest demonstrations of this behavior, but not necessarily the only one. This realization shifts the narrative away from exception and toward pattern recognition. It encourages a broader view in which abrupt change is treated as an inherent possibility rather than an outlier. Within this view, the question is not whether sudden resets can occur, but under what conditions they are most likely. As this chapter advances, the focus turns toward synthesis. Having examined evidence, mechanisms, and constraints, the remaining task is to integrate these strands into a coherent understanding. Not an answer that closes debate, but a framework that explains why the Younger Dryas unfolded as it did, and why similar dynamics may have shaped other moments in Earth's deep and recent past. That synthesis begins with acknowledging complexity without surrendering clarity. The Younger Dryas cannot be reduced to a single mechanism, yet its behavior follows recognizable rules. Rapid change occurred when long-term trends and short-term disturbances overlapped. Feedbacks amplified the initial shift. Stabilizing forces eventually reasserted themselves, restoring a different equilibrium. This sequence mirrors patterns observed in many complex systems beyond climate. Systems with multiple interacting components often resist change until pressures accumulate, then respond abruptly. Once reconfigured, they may remain stable in the new state until opposing forces become dominant. The Younger Dryas fits this pattern closely, reinforcing the interpretation that it reflects intrinsic system dynamics rather than an anomaly imposed from outside. Within this framework, debated triggers assume a different role. They are no longer required to explain everything, only to explain initiation. Internal dynamics account for persistence, feedbacks explain amplification, recovery follows when conditions reverse. This layered understanding accommodates uncertainty while preserving explanatory power. It also clarifies why the event remains so influential. The Younger Dryas is not simply an example of past climate variability. It is a demonstration of how quickly large-scale systems can change when thresholds are crossed. This demonstration challenges assumptions rooted in gradualism and invites more careful attention to transitions. The implications extend beyond geology. For early human populations, living within such a system would have required adaptability rather than prediction. Knowledge systems, movement patterns, and resource strategies would have needed to remain flexible. Cultural memory, shaped by such conditions, may emphasize disruption and renewal over stability. Yet the evidence remains grounded. There is no need to project modern anxieties backward or to interpret the Younger Dryas as a singular turning point for humanity. Its significance lies in what it reveals about environmental context, not in claims about global catastrophe or universal collapse. As this chapter nears completion, the Younger Dryas stands as a measured conclusion. Rapid, large-scale reorganization did occur. It was driven by convergence rather than dominance. It left clear physical traces and more subtle cultural implications. With this understanding established, the series is prepared to move forward. The next chapter will focus more narrowly on one debated possibility, examining it not as an explanation for everything, but as a test case for how external influences might intersect with sensitive systems, and how such intersections are evaluated within the discipline of evidence. That test case serves a specific purpose. It is not introduced to elevate one hypothesis above others, but to examine how scientific uncertainty is handled when evidence is partial and interpretations diverge. The Younger Dryas offers a rare opportunity to observe this process in detail because the event is both well documented and not fully explained. In this context, debate is not a flaw. It is a signal that evidence has reached a level where finer distinctions matter. When data is sparse, disagreement is often broad and speculative. When data improves, disagreements become narrower and more technical. The Younger Dryas now occupies this latter stage, where discussions focus on magnitudes, timings, and interactions rather than existence. This shift is evident in how proposed triggers are evaluated. Rather than asking whether a given mechanism could theoretically cause cooling, researchers ask whether it aligns with observed sequences. Did it occur at the right time? Could it operate at the required speed? Does it leave traces consistent with what is found in the record? Each question filters possibility into plausibility. Through this filtering, extreme scenarios tend to fall away. Explanations that require effects not observed are constrained or rejected. Those that fit within known physical limits remain, even if incompletely understood. This process does not produce certainty, but it does produce discipline. The Younger Dryas therefore becomes a teaching example. It shows how science advances not by declaring final answers, but by progressively narrowing the space of uncertainty. Each refinement sharpens the picture, even if some edges remain blurred. This perspective is essential for interpreting ancient resets responsibly. It avoids the temptation to fill gaps with narrative. Instead, it respects what the evidence can and cannot support. The Younger Dryas is compelling precisely because it resists simple storytelling. Its power lies in restraint. As this chapter continues toward its conclusion, the emphasis remains steady. Speed mattered. Scale mattered. The interaction of systems mattered. These facts are established. The remaining uncertainty does not undermine them. It contextualizes them. With that balance in place, the series prepares to transition. The focus will move from broad synthesis to focused examination, carrying forward the discipline established here. Not to resolve every debate, but to understand how such debates illuminate the structure of Earth's history, one abrupt shift at a time. That structure becomes clearer when the Younger Dryas is positioned at the threshold between description and interpretation. Description establishes what happened. Interpretation asks what it means. The strength of this event lies in how firmly the first is grounded, allowing the second to proceed with caution rather than speculation. By now, several conclusions are secure. Around 12,900 years ago, Earth's climate shifted abruptly toward colder conditions. This shift occurred far faster than long-term orbital forcing would predict. It persisted for over a millennium, and it ended just as rapidly, returning the planet to a warming trajectory. These features are not inferred loosely. They are recorded independently across ice, ocean, land, and biological archives. What remains open is not whether the Younger Dryas occurred, but how its various components interacted. Meltwater disruption explains much of the regional cooling. Feedbacks explain persistence. Threshold behavior explains speed. External influences remain possible, but constrained. No single mechanism is required to carry the full explanatory weight. This layered understanding reframes the idea of a reset. The Younger Dryas did not erase the past. It altered direction. It interrupted momentum. It forced reorganization. In doing so, it demonstrates that Earth systems can change state decisively without descending into chaos or requiring extraordinary causes. Such a realization has implications beyond this single event. It suggests that abrupt change is not an exception carved into the margins of history, but a recurring feature that emerges under specific conditions. These conditions are now better understood because of the Younger Dryas, even if they are not yet fully predictable. As this section of the 3I Atlas series closes, the narrative remains intentionally measured. The evidence does not support alarmism. It supports attentiveness. It calls for recognition of sensitivity, timing, and interaction rather than fear of unknown forces. The Younger Dryas stands, then, not as a final answer, but as a boundary marker. On one side lies a view of Earth shaped only by slow, continuous change. On the other lies a more complex reality, where long stability can give way to rapid transformation when thresholds are crossed. It is across that boundary that the next phase of the investigation begins. With the foundation established, attention will turn to one of the most debated possibilities raised by this event, examined not for its drama, but for what it reveals about how science approaches uncertainty when the record speaks clearly about speed, but only partially about cause. That next phase begins by revisiting the moment of transition itself. The onset of the Younger Dryas is not marked by gradual preparation in the record, but by a sharp boundary. In ice cores, chemical ratios shift abruptly. In sediments, biological communities reorganize within a narrow stratigraphic band. These markers suggest that whatever initiated the change acted faster than many of the processes it disrupted. This observation has important implications. It indicates that the trigger did not operate slowly over centuries, but delivered its influence within years or even months. Yet the consequences unfolded over far longer spans. This mismatch between initiation and outcome is a defining feature of the event and one that any explanation must respect. To understand this dynamic, researchers distinguish between forcing and response. Forcing refers to the initial push, however brief. Response encompasses the cascading adjustments that follow. In the Younger Dryas, the response dominates the record. Once cooling began, feedbacks involving ice growth, ocean circulation, and atmospheric patterns sustained it long after the initial disturbance had passed. This distinction helps explain why direct evidence for the trigger itself may be sparse. A short-lived event leaves a thinner trace than a millennium of altered climate. Its signature may be subtle, localized, or partially erased by the very processes it set in motion. This does not imply absence, but it does complicate detection. It also reinforces the need for precision. Claims about initiation must be evaluated against the narrow temporal window available. Broad correlations are insufficient. Timing must align closely. Spatial distribution must be plausible. Physical mechanisms must operate within known limits. In this sense, the Younger Dryas becomes an exercise in methodological discipline. It demands careful separation of cause and effect and constant awareness of scale. Large outcomes do not guarantee large beginnings. They reflect systems capable of amplification. As the investigation continues, the focus remains fixed on this narrow window of initiation, not to resolve it conclusively, but to understand its constraints. Because within those constraints lies the key insight of the Younger Dryas, that Earth's most dramatic shifts may begin quietly, at the edge of detectability, before unfolding into changes that reshape the trajectory of history itself. At the edge of detectability, evidence often takes the form of anomalies rather than certainties. Subtle deviations in chemistry, unusual concentrations of materials, abrupt shifts that resist simple explanation. In the context of the Younger Dryas, these anomalies cluster tightly around the boundary layer marking its onset, drawing attention precisely because they stand out against otherwise stable records. Researchers approach such anomalies cautiously. The first task is always verification. Are the signals real? Are they reproducible? Do they appear in multiple locations? Only when these conditions are met does interpretation begin. This process has been especially rigorous in the study of the Younger Dryas, given the implications attached to any proposed trigger. One of the challenges lies in separating coincidence from causation. Geological records are complex. multiple processes can operate simultaneously, producing overlapping signals. An anomaly that aligns in time with climate change may be related, or it may be incidental. Distinguishing between these possibilities requires cross-comparison across independent datasets. This is why the Younger Dryas debate has persisted. Some signals appear compelling in certain regions, yet are absent or muted in others. Some markers are replicated by multiple teams. Others remain contentious. Each new dataset refines the picture, but rarely resolves it entirely. What remains consistent is the narrowness of the transition. The boundary itself is thin. In many records, it is measured in centimeters, sometimes less. This thinness reinforces the conclusion that change was rapid. It also limits how much evidence can be preserved from the initiating moment itself. As a result, the Younger Dryas challenges conventional expectations about proof. It demonstrates that absence of overwhelming evidence does not equate to absence of process. Instead, it reflects the reality that brief events leave brief traces, especially when followed by long periods of reorganization. This understanding tempers both skepticism and certainty. It cautions against dismissing possibilities solely because evidence is subtle. At the same time, it demands restraint in interpretation. Subtlety requires proportionate claims. In this balanced space, the Younger Dryas continues to serve as a guide. It shows how science navigates the tension between what is known and what is inferred. And it underscores a quiet truth that some of the most consequential changes in Earth's history may be initiated by moments that are nearly invisible, discernible only through careful attention to the smallest deviations in an otherwise steady record. Those small deviations invite a shift in perspective. Instead of searching for definitive signatures of a single cause, researchers increasingly ask whether the boundary itself reflects a convergence of stresses reaching a tipping point. In this view, the anomalies observed at the onset of the Younger Dryas are not isolated signals pointing outward, but indicators of a system already under strain. The late glacial world was characterized by imbalance. Ice sheets were thinning unevenly. Meltwater pathways shifted repeatedly as ice margins advanced and retreated. Atmospheric circulation adjusted to changing temperature gradients between equator and pole. Each adjustment introduced variability, and together they created a climate state that was neither fully glacial nor fully interglacial. In such a state, stability becomes conditional. The system may appear steady, yet respond disproportionately to relatively minor disturbances. This behavior is well documented in complex systems theory. Near a threshold, fluctuations grow larger, recovery slows, and the system becomes increasingly sensitive to perturbation. Applied to the Younger Dryas, this framework suggests that the initiating disturbance may not need to be exceptional. It may only need to occur at the wrong moment. A freshwater pulse slightly larger than previous ones, a short-lived atmospheric shift, a brief external input. Any of these, arriving when feedbacks were aligned, could have tipped the balance. This interpretation aligns with the heterogeneity of the evidence. It explains why no single marker is universal and why different regions record different aspects of the transition. The change was system-wide, but its expression was locally modulated by geography, circulation, and existing conditions. Importantly, this does not dilute the significance of the event. It clarifies it. The Younger Dryas becomes an example of emergent behavior, where large outcomes arise from interactions rather than from singular forces. Its lesson lies not in identifying a dramatic cause, but in understanding vulnerability. As this chapter advances, the focus remains disciplined. The evidence points to rapid change, sustained by internal feedbacks, initiated under conditions of heightened sensitivity. This combination is sufficient to explain much of what is observed, even if the precise trigger remains uncertain. The value of the Younger Dryas, then, is not that it resolves ancient questions, but that it reframes them. It shifts attention away from extraordinary explanations and toward the architecture of change itself, toward the quiet moments when balance erodes, thresholds approach, and the conditions for sudden transformation are already in place, waiting for a final, almost imperceptible push. That final, almost imperceptible push is what keeps the Younger Dryas at the center of continued investigation, not because it demands a dramatic answer, but because it demonstrates how limited our resolution can be when studying rapid transitions deep in time. The closer science moves toward understanding such moments, the more it encounters the boundary between measurable signal and lost detail. This boundary is not unique to the Younger Dryas. It appears wherever processes unfold faster than the sediments that record them. Annual layers compress. Short events blur into single horizons. Later disturbances overwrite earlier ones. What remains is an outline rather than a complete image. Yet even outlines can be instructive. In the case of the Younger Dryas, the outline is unmistakable. A stable trajectory toward warming was interrupted. Cooling began abruptly. Systems reorganized. Stability returned in a new configuration. This sequence repeats across archives, reinforcing confidence in the core narrative even as finer details remain contested. The challenge, then, is not to force resolution where the record cannot provide it, but to work within those limits. This is why interpretations that emphasize convergence and sensitivity have gained traction. They require fewer assumptions and align more closely with what the data can support. Within this approach, the role of debated triggers becomes conditional rather than central. They are evaluated not as sole causes, but as potential contributors whose influence depends on timing and context. This framing allows scientific discussion to proceed without polarization, acknowledging uncertainty without surrendering rigor. It also reframes how sudden change is perceived. The Younger Dryas does not suggest that Earth is fragile in a simplistic sense. It suggests that Earth is responsive, capable of absorbing stress for long periods, then adjusting rapidly when conditions align. This responsiveness is neither inherently dangerous nor reassuring. It is simply a property of complex systems. As the chapter continues toward its final perspective, the Younger Dryas stands as a measured conclusion. It provides physical evidence that rapid climate reorganization has occurred. It demonstrates the importance of thresholds and feedbacks, and it highlights the limits of certainty when studying brief but consequential moments in deep time. What remains is not a mystery-demanding resolution, but a framework that informs future inquiry. A reminder that understanding Earth's past requires attention not only to long trends, but to the brief intervals where balance shifts and history quietly takes a different course. That different course, once taken, leaves lasting consequences even after conditions stabilize. The Younger Dryas did not simply pause the transition out of the Ice Age. It altered the sequence by which environments, ecosystems, and human populations moved forward. When warming resumed, it did so from a changed baseline, shaped by centuries of cold and adaptation. This is an often overlooked aspect of abrupt events. Even when recovery is rapid, the system does not return to its previous state. Path dependence matters. Species distributions shift. Soils develop differently. Coastlines move. Human groups reorganize their relationships with landscape and resources. The post-Younger Dryas world was not a continuation, but a re-entry. In climate records, this is visible in subtle ways. The warming that followed the Younger Dryas did not simply mirror the warming that preceded it. Atmospheric composition, ocean circulation patterns, and ice extent followed new trajectories. The system had learned, in a sense, responding differently after having passed through instability. For human populations, this re-entry coincides with profound developments. The early Holocene marks the spread of agriculture, more permanent settlements, and increasingly complex social structures in multiple regions. While these changes cannot be attributed solely to the Younger Dryas, they unfolded in a world shaped by its aftermath. Environmental predictability returned, but it was a predictability informed by recent disruption. This context adds depth to how ancient transitions are interpreted. The Younger Dryas does not stand as a singular cause of cultural change, but as a conditioning event. It narrowed options, tested resilience, and influenced the pathways that followed. In doing so, it becomes part of the background against which later developments emerged. From a scientific standpoint, this reinforces the importance of sequence. Events matter not only for what they do in the moment, but for how they reorder possibilities afterward. The Younger Dryas reshaped the boundary conditions of the early Holocene, influencing trajectories long after its end. As this chapter moves closer to conclusion, the focus remains steady. The Younger Dryas is best understood not as an anomaly, not as a catastrophe, and not as a complete reset, but as a rapid reorganization with lasting effects. Its significance lies in what it reveals about the tempo of change and the persistence of consequence. With that understanding, the investigation is prepared to transition. The remaining task is not to extract certainty from ambiguity, but to carry forward the lessons of the Younger Dryas into the next inquiry, where questions of external influence will be examined within the disciplined framework established here. Carrying those lessons forward requires resisting the urge to overextend them. The Younger Dryas does not become more meaningful by being made universal. Its value lies in specificity. It shows how rapid change can occur under particular conditions, not that such change is constant or inevitable. This distinction is essential for maintaining credibility. Within the scientific record, abrupt events are real but infrequent. Most of Earth's history is governed by slower processes that allow systems to adjust gradually. The Younger Dryas stands out precisely because it departs from this norm. Treating it as representative of all change would misread its importance. Treating it as impossible would ignore the evidence. This balanced interpretation has guided recent research. Instead of framing the Younger Dryas as a warning or a singular anomaly, it is increasingly used as a calibration point. Models are tested against its speed. Hypotheses are measured against its duration. The event becomes a reference for what is physically plausible rather than a template for expectation. In this way, the Younger Dryas helps refine the boundaries of understanding. It narrows the range of acceptable explanations for abrupt change and improves the ability to distinguish between coincidence and causation. It also highlights the importance of interdisciplinary evidence, where climate data, geological markers, and archaeological records are considered together rather than in isolation. This integration does not eliminate uncertainty, but it reshapes it. Uncertainty becomes structured rather than open-ended. Certain pathways are ruled out, others remain viable but constrained. The conversation moves from speculation to refinement. As this process unfolds, the Younger Dryas continues to exert influence not through drama, but through discipline. It reminds researchers that evidence must lead interpretation, not the reverse. It also reminds them that even the most carefully constructed explanations must remain provisional when dealing with events compressed into narrow slices of time. Approaching the close of this chapter, the Younger Dryas stands as a measured conclusion. It confirms that rapid, large-scale reorganization has occurred in Earth's past. It demonstrates that such change can arise from convergence rather than singular cause, and it reinforces the importance of restraint when interpreting incomplete records. The investigation now turns its attention forward. With the framework established, the next chapter will examine one debated possibility in isolation, not to elevate it, but to test how it fits within the constraints defined here. In doing so, it continues the larger inquiry into how sudden shifts emerge, persist, and fade within the long continuity of Earth's history. That larger inquiry gains clarity as the focus narrows. Having established the conditions under which rapid reorganization can occur, attention can now be directed toward a single line of debate without losing balance. The purpose is not to argue for a cause, but to examine how such causes are evaluated when evidence is partial and consequences are significant. In the case of the Younger Dryas, this approach has revealed an important methodological shift. Earlier discussions often treated competing explanations as mutually exclusive. Meltwater disruption or external input, internal dynamics or external forcing. Over time, this framing has softened. The evidence increasingly supports interaction rather than opposition. This does not mean all ideas carry equal weight. It means that viable explanations must complement rather than replace established processes. Any external influence, if present, would need to act within a system already predisposed to change. It would not override internal dynamics, but intersect with them. This reframing has practical consequences. It directs research toward identifying moments of overlap when internal sensitivity and external disturbance coincide. It also shifts emphasis toward high-resolution records that can resolve timing with greater precision. The closer science can approach the moment of initiation, the more clearly these interactions can be evaluated. The Younger Dryas remains a challenge precisely because that moment is so brief. The boundary layer captures the outcome of change more clearly than its beginning. Yet even this limitation offers insight. It reinforces the idea that initiation may be subtle, easily masked by the processes it sets in motion. Within this context, restraint remains essential. Hypotheses are strongest when they explain more than they assume. The Younger Dryas record rewards explanations that respect scale, timing, and preservation, and it resists those that rely on singular dramatic events unsupported by corresponding traces. As the chapter approaches its final perspective, the narrative remains grounded. The Younger Dryas does not demand resolution to remain meaningful. Its value lies in what it reveals about the behavior of complex systems under stress, and about the careful balance required when interpreting deep time. With this foundation complete, the investigation is ready to move forward. The next chapter will examine a specific debated mechanism in greater detail, applying the same discipline used throughout this discussion, not to confirm a conclusion, but to understand how evidence, uncertainty, and interpretation converge when Earth's history accelerates beyond the pace of ordinary change. That convergence marks the natural close of this chapter. The Younger Dryas has been examined not as an isolated curiosity, but as a structured event defined by evidence, limits, and disciplined interpretation. Its significance lies not in what it proves conclusively, but in what it demonstrates clearly. That Earth's climate system is capable of rapid, coordinated change when conditions align. By tracing the event from onset to recovery, a consistent picture emerges. Long-term warming created instability. Feedbacks amplified disturbance. Thresholds were crossed. A new state persisted until balance shifted once more. Each phase is supported by independent lines of evidence, even if the initiating moment remains partially obscured. This structure allows the Younger Dryas to function as a reference, rather than a riddle. It anchors discussion of abrupt change in measurable reality. It shows that speed and scale can coexist without catastrophe, and it establishes constraints within which more speculative ideas must operate if they are to remain credible. Importantly, the event also illustrates the limits of certainty. Some questions remain open not because of oversight, but because of the nature of the record itself. Brief moments leave brief traces. Interpretation must therefore remain proportional to preservation. This balance between confidence and restraint is one of the clearest lessons the Younger Dryas offers. As the chapter closes, the focus shifts away from description and toward inquiry. Having established that rapid reorganization occurred, the next step is to examine how proposed external influences are evaluated within this framework. Not as explanations in search of validation, but as test cases for how science navigates uncertainty at the boundary of resolution. The Younger Dryas does not end the investigation, it sharpens it. It defines the questions that follow and the standards they must meet. And in doing so, it prepares the ground for the next chapter of the 3I Atlas series, where one of the most debated possibilities will be examined directly, measured not by its appeal, but by how well it withstands the constraints imposed by evidence, timing, and scale. With that groundwork in place, the investigation enters a more interpretive phase, not a departure from evidence, but a closer examination of how evidence is framed when certainty cannot be complete. This is where the Younger Dryas begins to function not only as a climatic event, but as a lens through which scientific reasoning itself can be observed. Interpretation becomes necessary when data reaches its natural limits. The records describe what happened with clarity, but not every step of how it happened. Bridging that gap requires models, comparisons, and assumptions that must remain visible and testable. The Younger Dryas is particularly valuable here because it sits at the edge of what can be resolved, making those assumptions easier to examine. One of the central interpretive questions concerns proportionality. How much cause is required to produce how much effect? The Younger Dryas challenges intuitive answers. A relatively brief disturbance appears to have initiated centuries of altered climate behavior. This mismatch forces a reconsideration of scale, suggesting that system response can far exceed initial input when feedbacks are aligned. This has led researchers to distinguish between primary drivers and secondary amplifiers. Primary drivers initiate change. Secondary processes determine its extent and duration. In the Younger Dryas, internal amplifiers clearly played a dominant role. The open question is how much force was required to activate them. This distinction is crucial because it reframes debate. Instead of asking whether a proposed trigger explains everything, the question becomes whether it plausibly explains initiation. The burden of explanation is redistributed. Persistence belongs to feedbacks. Speed belongs to thresholds. Initiation belongs to disturbance, whether internal or external. Such reframing reduces polarization. It allows competing ideas to be evaluated within a shared structure rather than as opposing narratives. Meltwater disruption, atmospheric shifts, and possible external inputs are no longer mutually exclusive. They become variables whose influence depends on timing and context. In this interpretive space, restraint remains the guiding principle. The Younger Dryas does not invite grand conclusions. It invites careful alignment between claim and evidence. Its lesson is not that science has failed to explain the past, but that explanation itself is a layered process, moving from observation to constraint to probability. As this phase unfolds, the focus shifts from what the Younger Dryas was to what it teaches about how sudden change is understood, not as a single answer waiting to be discovered, but as a structured question that sharpens with each new line of evidence, even as some uncertainty remains. That structured question leads naturally to theory, not theory as speculation, but as a framework for organizing what is known and what remains unresolved. In the case of the Younger Dryas, theory helps bridge the gap between clear outcomes and uncertain beginnings, offering a way to test plausibility without overstating confidence. One of the most influential theoretical lenses applied to the Younger Dryas is nonlinear dynamics. In such systems, change does not scale smoothly with input. Small disturbances can produce negligible effects under stable conditions, yet trigger major transitions when thresholds are near. This behavior is not exceptional. It is observed in physical, biological, and social systems alike. Applied to climate, nonlinear dynamics help explain why the Younger Dryas could emerge so abruptly. The system did not need a large, sustained forcing. It needed a push at the wrong moment. Once the threshold was crossed, feedbacks took over, sustaining the new state until conditions shifted again. This framework aligns closely with the evidence. It explains why no single dramatic trigger is required. It accounts for the mismatch between short initiation and long persistence, and it accommodates regional variability within a globally coordinated shift. Theory, in this case, does not replace data. It organizes it. Crucially, this approach also defines limits. Not every abrupt event can be explained this way. Threshold behavior requires specific preconditions. The Younger Dryas occurred during a period of deglaciation, when ice volume, ocean circulation, and atmospheric composition were all in flux. Outside such contexts, similar disturbances might produce little effect. This conditionality reinforces restraint. It prevents the Younger Dryas from being misused as a universal explanation. Instead, it becomes an example of how context determines outcome. The same disturbance that triggers rapid change under one set of conditions may be absorbed quietly under another. As theory and evidence align, the Younger Dryas takes on a different significance. It is no longer a puzzle demanding resolution, but a demonstration of principle. It shows how abrupt change can emerge naturally from complex interactions without requiring extraordinary assumptions. With this theoretical foundation in place, the investigation approaches its final interpretive turn. The remaining task is not to prove a cause, but to reflect on what this event reveals about the architecture of Earth's history itself. A history shaped not only by slow accumulation, but by moments when balance gives way and the system chooses a new path with surprising speed. That architecture becomes more apparent when viewed across longer spans of time. Earth's history is often summarized through averages, trends, and cycles that smooth over abrupt transitions. Yet events like the Younger Dryas reveal a different texture beneath those summaries. They show that history is not only shaped by gradual motion, but by brief moments when direction changes decisively. These moments are difficult to integrate into linear narratives. They resist simple cause and effect, and they compress consequences into windows that feel disproportionate to their duration. The Younger Dryas is one such moment. It occupies a narrow band of time, yet its imprint extends far beyond its chronological limits, influencing how subsequent change unfolded. This perspective encourages a reevaluation of continuity. Rather than imagining Earth's past as a continuous flow occasionally interrupted by anomalies, it becomes possible to see abrupt events as integral components of that flow. They are not errors in the record. They are expressions of how complex systems behave when pushed beyond balance. Within this view, the Younger Dryas is neither exceptional nor commonplace. It is conditional. It occurs when long-term processes create vulnerability and short-term disturbances exploit it. This interplay produces change that is rapid, coherent, and consequential, yet still bounded by physical limits. Understanding this interplay has practical implications for how past events are compared. Similar outcomes do not require identical causes. What matters is whether systems share comparable states of sensitivity. When they do, different triggers can produce similar results. When they do not, even dramatic disturbances may leave little trace. The Younger Dryas therefore serves as a bridge between specific history and general principle. It grounds abstract theory in physical evidence and anchors broad interpretation in a well-documented case. Its value lies in how it connects scales, linking brief moments to long-term trajectories. As this chapter moves toward its final reflections, the emphasis remains measured. The Younger Dryas does not redefine Earth's history. It refines understanding of how that history unfolds. It reminds us that pace matters, that thresholds matter, and that the most consequential changes may occur not at the extremes, but at moments of transition when balance is already fragile. With that realization, the investigation approaches its closing perspective, not with resolution but with clarity, a clearer view of how sudden change fits within continuity and how the past preserves not only what endured, but the moments when endurance was tested and the course of history quietly shifted. That quiet shift is the final thread running through the Younger Dryas. It is not remembered in the record as a singular catastrophe, but as a transition that unfolded faster than the systems it altered were accustomed to handling. Its power lies in contrast. A world moving steadily toward warmth abruptly turned back toward cold, not for a moment, but for centuries. This contrast sharpens how evidence is read. Without the surrounding trend of deglaciation, the Younger Dryas might appear less remarkable. It is the interruption itself that gives it meaning. It reveals how quickly expectations based on long-term patterns can fail when thresholds are crossed. From this standpoint, the event becomes a lesson in humility. Even with extensive data, precise dating, and sophisticated models, certain aspects remain beyond resolution. Not because the tools are flawed, but because the past does not preserve every detail evenly. What is preserved must therefore be interpreted with care. The Younger Dryas exemplifies this balance between knowledge and limitation. It is one of the best documented abrupt climate events in Earth's history, yet its initiating moment remains partially obscured. This coexistence of clarity and uncertainty is not a contradiction. It is a realistic reflection of how deep time is recorded. Rather than weakening the case, this tension strengthens it. It demonstrates that science can operate confidently without demanding total certainty. It can establish boundaries, test hypotheses, and refine understanding while acknowledging what cannot yet be known. As this interpretive phase draws toward completion, the Younger Dryas stands as a measured conclusion. Rapid, large-scale climate reorganization occurred. It was sustained by internal feedbacks. It emerged from a context of instability, and it left lasting consequences that shaped what followed. What remains is not a question of belief, but of perspective. Whether the Younger Dryas is seen as an anomaly or as a feature of complex systems depends on how history is framed. Seen closely, it is a disruption. Seen broadly, it is a pattern. And it is from this broader view that the chapter prepares to close, carrying forward a single quiet insight: that Earth's history is not written only in slow change, but in moments when balance gives way, direction shifts, and the future unfolds along a path that, just moments before, did not yet exist. That newly chosen path is often invisible at the moment it begins. In the case of the Younger Dryas, no single marker announces the future it would create. The boundary layer records change, but not intention. Only in retrospect does its significance become clear, as subsequent developments unfold from the conditions it imposed. This retrospective clarity is a common feature of abrupt events. Their meaning is rarely apparent in real time. It emerges later, through consequence. For the Younger Dryas, those consequences include altered ecosystems, shifted coastlines, and a restructured early Holocene world that followed its end. Understanding this delayed significance helps explain why such events resist simple interpretation. The cause may be brief, the evidence subtle, but the effects propagate forward, shaping outcomes long after the initiating moment has passed. In this way, the Younger Dryas functions less like an episode and more like a hinge, a point where the direction of change pivoted. This hinge perspective aligns with the broader narrative of Earth's climate history. Major transitions are often marked not by extremes, but by reversals, points where prevailing trends are interrupted and redirected. The Younger Dryas represents such a reversal, a temporary return to cold that restructured the pathway toward interglacial stability. From a scientific standpoint, this reinforces the importance of sequence. What matters is not only what happened, but when it happened relative to other processes. The Younger Dryas occurred at a moment when ice retreat, sea level rise, and human expansion were already underway. Its timing amplified its impact. This sensitivity to timing is central to understanding abrupt change. Identical conditions at a different moment might produce a different outcome. The Younger Dryas is therefore inseparable from its context. It cannot be abstracted without losing meaning. As the chapter moves toward its final blocks, the emphasis remains on integration. Evidence, theory, and interpretation converge on a consistent conclusion. Rapid climate reorganization occurred. It was conditional. It left lasting consequences. And it reveals something fundamental about how complex systems behave near thresholds. With this convergence complete, the narrative begins to release its focus. not toward final answers, but toward reflection. The Younger Dryas does not close inquiry. It refines it, leaving behind a clearer understanding of how moments of sudden change are woven into the long continuity of Earth's history. That reflection naturally turns inward, toward how knowledge itself adapts to events like the Younger Dryas. Science, like climate, advances unevenly. Long periods of incremental progress are occasionally interrupted by moments when evidence forces a shift in perspective. The recognition of abrupt climate change is one such moment, and the Younger Dryas played a central role in bringing it into focus. Before this event was fully understood, climate history was often framed as a sequence of slow, predictable transitions. The Younger Dryas challenged that framing not through theory, but through data. Its clarity made dismissal impossible. Ice cores did not suggest gradual cooling. They recorded a sharp break. Sediments did not show slow ecological drift. They showed rapid turnover. This forced a recalibration. Models were revised. Assumptions were questioned. New tools were developed to resolve faster change. In this way, the Younger Dryas influenced not only how Earth's past is understood, but how it is studied. It sharpened attention to resolution, timing, and feedbacks, reshaping methodology as much as interpretation. This methodological legacy is part of the event's enduring importance. It demonstrates how a single, well-documented interval can alter an entire field's approach. The Younger Dryas became a benchmark against which both data quality and theoretical robustness are measured. At the same time, it serves as a reminder of limits. Even with improved tools, certain aspects remain elusive. The initiating moment still resists full reconstruction. Competing hypotheses persist. This persistence is not failure. It is a sign that inquiry has reached the boundary of what current evidence can support. As the chapter approaches its closing phase, the Younger Dryas stands as both lesson and reference. It teaches that rapid change is possible. It shows how systems respond when thresholds are crossed. And it illustrates how knowledge evolves in response to clear, challenging evidence. The narrative now begins its final descent, away from analysis and toward quiet synthesis. What remains is not an argument to be won, but an understanding to be carried forward, that Earth's history includes moments when balance shifts suddenly, and that recognizing those moments requires patience, restraint, and attention to the smallest traces left behind by rapid change. That quiet synthesis brings the focus back to scale. The Younger Dryas occupies a relatively brief span in geological time, yet its study reaches outward, influencing how much older and much younger events are interpreted. It has become a lens through which abrupt change is recognized elsewhere, even when the evidence is less complete. In this way, the event reshapes expectations. Researchers no longer assume that absence of gradual preparation implies absence of process. Instead, they recognize that some changes occur faster than conventional records were once thought capable of preserving. This recognition has expanded the search for abrupt transitions beyond the obvious, encouraging closer inspection of boundaries that were previously overlooked. The Younger Dryas also refines how caution is applied. It demonstrates that restraint does not mean avoidance of difficult questions. It means aligning conclusions with what the evidence can support, even when that evidence points toward uncomfortable complexity. The event is compelling precisely because it does not resolve neatly. It demands patience rather than certainty. This patience is essential when approaching ideas of resets. The Younger Dryas shows that reorganization can be profound without being total. Systems change state, but continuity remains. Life persists. Processes continue. What shifts are the conditions under which those processes operate. Such a view tempers extremes. It avoids portraying the past as a sequence of collapses, while also avoiding the assumption of uninterrupted stability. The Younger Dryas exists between those poles, a moment of disruption embedded within continuity. As the chapter approaches its final blocks, the emphasis settles into reflection rather than analysis. The event has been examined from multiple angles, not to exhaust it, but to understand its shape, speed, scale, sensitivity. These are the defining features that remain when interpretation is stripped back to essentials. What the Younger Dryas ultimately offers is perspective. It reminds us that history, whether geological or human, is not governed solely by averages. It is shaped by moments when balance shifts, when accumulated pressures find release, and when the future takes a direction that could not have been predicted from the calm that preceded it. With this perspective in place, the narrative prepares to close, not with finality, but with continuity. The inquiry does not end here. It moves forward, informed by the lessons of a time when the Earth changed course quickly, quietly, and in ways that continue to shape how its past is understood. That continuity is the final thread binding this chapter together. The Younger Dryas does not conclude with certainty, but with orientation. It points attention toward how change unfolds, rather than toward any single explanation for why it began. In doing so, it leaves behind a framework that extends beyond one event and into the broader rhythm of Earth's history. At its core, the Younger Dryas demonstrates that stability is conditional. Long trends can persist for millennia, giving the impression of predictability, yet still be interrupted when thresholds are crossed. These interruptions are not random. They arise from the interaction of forces already in motion, converging at moments when balance is narrow and resilience is reduced. This understanding reshapes how past and future are connected. It suggests that history is not only cumulative, but punctuated. That long periods of relative calm may be followed by brief intervals of rapid reorganization, after which continuity resumes along a changed path. The Younger Dryas embodies this pattern with unusual clarity. Importantly, the event also reinforces the value of restraint. The evidence does not demand dramatic conclusions. It demands careful attention to speed, timing, and interaction. It shows that meaningful insight can emerge without complete resolution, and that uncertainty, when clearly defined, strengthens rather than weakens understanding. As this chapter nears its end, the Younger Dryas stands as a measured reference point. It confirms that abrupt climate change has occurred. It illustrates how internal dynamics and external influences may intersect, and it defines the limits within which interpretation must operate. What remains is not an answer, but a lens, a way of seeing Earth's past that accommodates both stability and sudden change, a recognition that thresholds matter, and that the moments when they are crossed can shape outcomes far beyond their brief duration. With this lens in place, the chapter gently releases its focus. The investigation does not stop. It transitions, carrying forward the lessons of the Younger Dryas into the next inquiry, where attention will turn more narrowly to one debated possibility, examined with the same discipline, the same restraint, and the same commitment to letting evidence speak first, even when it speaks softly. That soft voice of evidence is where reflection begins. After tracing mechanisms, constraints, and interpretations, the Younger Dryas settles into something quieter than explanation. It becomes a reminder of how Earth communicates change, not through single signals, but through convergence, not through certainty, but through consistency across many independent records. What emerges most clearly is not fear, but humility. The planet's history shows that rapid transformation is possible without spectacle, without collapse, and without warning in the way humans tend to expect it. The Younger Dryas unfolded within the normal operation of Earth systems, yet it altered trajectories that would shape everything that followed. This realization reframes responsibility. Understanding the past is not about assigning cause or blame, but about recognizing behavior. The Younger Dryas teaches that systems can appear stable while quietly approaching thresholds, That lesson applies backward into deep time and forward into any attempt to interpret change responsibly. For early human populations, this would have been lived rather than studied. They would not have known causes or mechanisms, only outcomes, seasons arriving differently, landscapes changing character, resources becoming unreliable and then stable again. Memory in such conditions becomes adaptive rather than precise. Seen this way, the Younger Dryas occupies a space between science and inheritance. It is fully grounded in physical evidence, yet its implications extend into how continuity is perceived across generations. It is not a story of ending, but of interruption and return. As the chapter begins its final descent, the emphasis remains calm. The Younger Dryas does not demand urgency. It invites attentiveness. It asks only that change be taken seriously, even when it occurs quietly and within the bounds of natural process. In this attentiveness, the investigation finds its closing rhythm, not by resolving every question, but by clarifying what kind of questions matter when studying moments that compress centuries of consequence into a brief and fragile boundary in time. That closing rhythm carries a final insight. The Younger Dryas shows that history does not always signal its turning points loudly. Some of the most consequential shifts arrive without spectacle, registered only in subtle changes that accumulate meaning over time. It is only later, through careful reconstruction, that their significance becomes clear. This understanding reshapes how endings and beginnings are perceived. The Younger Dryas did not announce the end of the Ice Age, nor did it prevent it. Instead, it interrupted the transition, introducing a pause that reshaped the conditions under which warming eventually resumed. The end result was not reversal, but redirection. In this sense, the event highlights a quiet truth about complex systems. Change does not require collapse to be transformative. Reorganization alone can alter trajectories. A system can remain intact, yet behave differently enough that its future unfolds along a new path. The Younger Dryas exemplifies this kind of transformation. This perspective encourages restraint when interpreting the past. It discourages narratives built on extremes and favors those grounded in process. The evidence does not support visions of sudden annihilation. It supports a subtler picture, one where thresholds are crossed, feedbacks engage, and the system adapts to a new configuration. As the chapter approaches its final block, what remains is a sense of continuity rather than conclusion. The Younger Dryas stands as a moment within a much longer story, important not because it ends anything, but because it reveals how transitions can unfold unexpectedly. The lesson it leaves behind is simple and enduring. Stability is not guaranteed by duration. Long calm does not preclude rapid change. And understanding the past requires attention not only to what persists, but to the brief intervals where persistence is tested. With this understanding, the narrative prepares to close gently. The investigation does not end with certainty, but with clarity of perspective. A recognition that Earth's history is shaped as much by moments of quiet reorganization as by long spans of apparent continuity, and that within those moments lie some of the most instructive insights into how change truly works. That clarity of perspective carries one final responsibility: to resist the temptation to turn understanding into prophecy. The Younger Dryas is often invoked in modern discussions because it demonstrates speed, but its value does not lie in prediction. It lies in recognition. Recognition that Earth's systems have behaved in ways that defy simple expectation, and that such behavior is part of their natural range. This recognition does not imply inevitability. The conditions that gave rise to the Younger Dryas were specific, tied to the unique configuration of ice, oceans, and atmosphere at the end of the last ice age. What it offers instead is a boundary of possibility, a demonstration of what can occur when sensitivity is high and balance is narrow. In this way, the event becomes a reference point rather than a warning. It grounds discussion of abrupt change in documented reality without extending that reality beyond what evidence supports. It teaches that humility and precision are not opposites, but partners in understanding deep time. The Younger Dryas also reminds us that the past is not a static archive. It is an active framework through which present questions are shaped. Each new discovery refines how earlier events are understood, and each reinterpretation adjusts the context in which future evidence will be placed. As this chapter nears its end, the narrative releases its analytical grip. What remains is a steady awareness that beneath long spans of gradual change, Earth's history includes moments when systems reorganize quickly, quietly, and decisively. Moments that leave behind boundaries in the record, thin layers where before and after no longer align. These boundaries do not demand belief. They invite attention to timing, to interaction, to the way small shifts, when aligned, can redirect the course of history without spectacle or collapse. With that awareness in place, the chapter prepares to conclude, not with answers fixed in place, but with a framework refined by evidence and restraint, a way of seeing the past that remains open, patient, and grounded in the quiet authority of what the record is able to preserve. That quiet authority is where the chapter finally rests. The Younger Dryas does not close with resolution, but with orientation. It leaves behind a clearer sense of how Earth changes, and how those changes are best understood, not as singular events demanding dramatic explanation, but as moments when complex systems briefly reveal their deeper structure. Across this investigation, one conclusion has remained consistent. Speed matters. The Younger Dryas is defined not by how cold it became, but by how quickly the shift occurred. That speed forces a reconsideration of assumptions about gradualism, stability, and predictability. It shows that history can pivot within spans short enough to be experienced, remembered, and passed forward. At the same time, restraint matters just as much. The evidence supports reorganization, not annihilation. It supports convergence, not singular catastrophe. It supports thresholds and feedbacks, not inevitability. Holding to these distinctions preserves credibility and allows understanding to deepen without distortion. In this balance, the Younger Dryas becomes more than an episode. It becomes a reference point for how inquiry proceeds when the record is clear about outcome, but partial about cause. It shows how science advances by narrowing uncertainty, not eliminating it. By aligning interpretation with evidence, even when that evidence speaks softly. As the chapter ends, the broader series continues. The foundation has been laid carefully, without urgency, without excess. What comes next will examine one debated possibility more closely, not to elevate it, but to test it within the disciplined framework established here. For now, the Younger Dryas remains what the record shows it to be. A moment when Earth changed course rapidly. A reminder that stability is conditional, and an invitation to look more closely at the thin boundaries in time where before and after no longer match, and where the quiet mechanics of change become briefly visible before receding once again into deep history.